Let's go back to the world of geometry for a moment. We have a right triangle whose acute angles are called alpha and beta. And we want to think about what these guys have in common with each other. Clearly, they're both acute angles, right? Because the right angle is half um, of the degrees that reside inside this triangle. So if 90 degrees is half of it, then these guys must be the other half of it, and they must add up to 90 degrees. So we know that the relationship here is that alpha plus beta equals 90 degrees, but we're kind of falling in love with this new unit of angle measurements, this idea of degrees. Radians. So instead of saying alpha plus beta equals 90 degrees, which isn't wrong, but I just want to kind of help us, get a better appreciation of radians. Let's stick with radians instead. So alpha plus beta also equals some number of radians. We know that that's pi over 2. That's the same thing as 90 degrees. All right, so this is a relationship between two different angles. Now, probably in geometry, you played around with SOHCAHTOA and you found some relationships, like, for example, sine of alpha, y over r. That's not very surprising. Cosine of alpha is x over r. Well, these are just the definitions that we learned at the beginning of the school year. But then we go to sine of beta. Sine of beta is now going to be x over r. Wait a second, I've seen x over r somewhere before. And the cosine of beta is y over r. Wait a second, y over r looks awfully familiar. Yeah, so we've got this thing going on where sine of alpha is the same thing as the cosine of beta. You probably saw this at one point in geometry. It's fairly obvious once you look at it. But if we think about this, think about what beta equals. Beta equals pi over 2 minus alpha. So we can say that this thing right here is the same thing as the cosine of pi over 2 minus alpha. So what we're really seeing here is that the sine of alpha is the same thing as the cosine of pi over 2 minus alpha. Okay. And then we can do the same thing over here. These are both equal to x over r. So instead of writing cosine of alpha, maybe I'll write that as the cosine of some other angle. Well, if beta equals pi over 2 minus alpha, then alpha must equal pi over 2 minus beta. That's easy. So we'll replace alpha with pi over 2 minus beta. And that's the same thing as the sine of beta. Okay, so that's interesting. It sure looks like cosine and sine are related in that the supplement angles give us the other function, okay? And this is the co-function identities. So what we're seeing here is if we take the sine of pi over 2 minus theta, that is the same thing as taking the cosine of theta. Call it alpha, call it beta, I don't care. We're going to call it theta. And if we take the cosine of pi over 2 minus theta, then we're going to call it sine of theta. And those are exactly what we're seeing over here. Replace the alphas with thetas, and we get this bottom identity right here. Replace the betas with thetas, and we get this top identity right here. And if those are true, then it's going to follow fairly easily that the other trig functions have similar co-function identities. Tangent goes to cotangent. Cotangent goes to tangent. Secant goes to cosecant. Cosecant goes to secant. All right, and that's one way we can kind of change this argument. If we have pi over 2 minus an angle, we can just talk about its complement angle. I think I said supplement earlier. I meant complement. The complement, the two that add up to 90 degrees or to a right angle. You can take the sine of one angle, or you can take the cosine of the complement of that angle. And all of those cofunction identities work the same way. So these are some somewhat useful identities that we're going to see from time to time. Here's another idea. Let's take a look at a generic angle theta graphed on the unit circle. And then I ask you, let's see, what if we can figure out where negative theta is? So this generic angle theta goes some partial rotation around the circle. If we wanted to find negative theta, then it would just go that same partial revolution in the opposite direction. So that would be negative theta. That's going in this direction. So that's what it's asking us to do. Sketch an angle whose measure is negative theta in that diagram. What are the coordinates of this point right here? Well, we're going to go to the left. I'm sorry, we're going to go to the right x, and we're going to go down the same distance we went up, so that's going to be a negative y value, right? So the cosine of theta is still the x coordinate here, but we have flipped the sign of the sign. We have changed the sign from positive to negative, so we're going to say negative sine of theta. All right, so, but that's also the same thing as if we think about points on the unit circle. That leads us to the idea that this is the same point as the cosine of negative theta, comma, the sine of negative theta. So this is kind of interesting. So what we're finding is that the cosine of theta and the cosine of negative theta are the same thing, right? These guys right here both represent the x-coordinate of this point. So the cosine of negative theta and the cosine of positive theta are the same thing. Well, that might be a little bit surprising, but we've seen functions like that before. Think about x squared. Negative 1 squared and positive 1 squared give us the same thing. Negative 7 squared and positive 7 squared give us the same thing. So cosine works the same way in that whether the input is negative or positive, it gives us the same answer either way. Whereas sine flips the sign. So sine of negative theta is the same thing as, let's use blue here, these guys are the same. They're both the y-coordinates of this point, so the sine of negative theta equals negative the sine of positive theta. Aha! So one of these functions is even and one of these functions is odd. So we'll talk about which one's which in a moment. Let's go ahead and see if we can figure out these other guys here. Let's see. So tangent, well, that's sine over cosine. So if I take the tangent of negative theta, that's the same thing as taking the sine of negative theta divided by the cosine of negative theta. But we just talked about how the sine of negative theta is the same thing as negative sine of theta. And we also just talked about how the cosine of negative theta is the same as the positive cosine of positive theta. So this looks like it's the same thing as negative sine over cosine or negative tangent of theta. We can do a very similar argument to see that the cotangent works the same way. Whereas when we get to the reciprocal functions, we can see that, well, the secant is the reciprocal of the cosine. So that one, let's go back to orange for that one, arbitrarily. I said orange, hold on. Gotta keep that color coding. The secant of positive theta. We can see that because it's the same property as the cosine, and they're just reciprocals of one another. Whereas the cosecant is the reciprocal of the sine, so that would be negative cosecant of positive theta. All right, so we've got 2 of the oranges and 4 of the blues. So that means that we can kind of group those together in odd versus even functions. Well, which one's which? You may recall, I hope you recall, because once upon a time you did learn that even functions were symmetric with respect to the y-axis. And what we saw is that if we plugged in a positive x or a negative x, we got the same answer, right? We got the same thing back again, just like the x squared function. Odd functions, on the other hand, were not symmetric with respect to the x-axis, which everyone guesses, oh, just flip the x to the y or the y to the x. No. That would be something that wouldn't be a function. Instead, we actually end up having negative x in the function is the same thing as taking negative of f of positive x. So x comma y goes to negative x, negative y. This ends up rotating around the origin. So this is symmetric with respect to the origin. And that's what odd functions end up doing. Think about x cubed. That's an odd function because if I cube 4 and if I cube negative 4, I get the same number just with opposite signs. So that's what the property of odd functions. All right. So what we're going to do now is we're going to try to combine both the co-function identities and the even-odd identities to figure out some of these guys down here. So let's start by noticing this nasty little trick. Notice that this looks an awful lot like the co-function identities. We'll scroll back up to double check those. I see a pi over 2, and I see a minus, and I see a theta, but the order got flipped, right? It's x instead of theta. Who cares what the variable is called? So we can't just flip the order of subtraction. We get a different number, right? So this is not the same thing as the cotangent of pi over 2 minus x, right? Because order matters with subtraction. But if we factor out a negative, then they are the same. All right, so this is cotangent of negative something. Well, cotangent of negative something is the same thing as negative of the cotangent of that positive something. So this is going to be an odd function. Cotangent is an odd function, so that negative can get pulled out. And then we're looking at the cotangent of pi over 2 minus x, but that's a co-function identity. We know that cotangent of pi over 2 minus x is the same thing as the tangent of x. But wait a second. Tangent of x equals negative 3.104. So if we take negative of negative 3.104, we end up with a positive 3.104. Fantastic. All right, so very little actual arithmetic here. It's just flipping the sign. But the reasoning is using the two different identities in conjunction with one another. We see the same trick going on here. We can't just flip the order of the subtraction, right? That changes the value from positive to negative or negative to positive. So we have to factor out that negative. And then we have cosine of negative something. But we just saw that cosine of negative something is the same thing as cosine of the positive of that same thing. So that means that we can just ignore this negative. It's almost like we're squaring a negative value and the negative goes away. That's what even functions do. It's not necessarily that we're squaring it, but we are we have an even function, and that's what even functions do. So now we have this cosine of pi over 2 minus alpha. This is the same thing as the sine of alpha based on our co-function identities, and we know that the sine of alpha is 0.922, and therefore we are done. I'll leave you with one parting thought here. If we graph the function cosine of x, just going back to this odd and even idea up here, if we graph the graph of cosine of x, remember it starts at a maximum, it goes down from there, and then it goes down to a minimum, it goes back up from there, and that's what one period looks like. But if we go the other way, we can see this symmetry with respect to the y-axis, right? If we fold this graph on the y-axis, we get a left half and a right half that are exactly the same. Whereas if we graph the sine graph, that starts at the midline and it goes up to a maximum, back down to the minimum, goes down to the minimum, goes back up to the center line. It does the same thing over here in reverse. And if we think about not slicing this in half, but actually kind of rotating this 180 degrees, flipping it around upside down, we're going to get the exact same graph back again. So that's kind of the graphical interpretation of these guys. On this one, if x comma y is on the graph, then negative x comma y is also on the graph. On this one, if x comma y is on the graph, then negative x comma negative y is on the graph. So that might help some of you guys visualize that property of even versus odd.